we have a secondary alcohol, right? That has a stereocenter. RS, doesn't matter. It's wedged. It's going to react with PBr3. When you see PBr3, you should see two things. Activation of alcohols, inversion. Right? It's going to make an alcoholic good leaving group, and it's going to add a bromine and do it in an SN2 way. So this first step, you're just going to get this. Of course, there's a mechanism, but we've seen that before. I'm not going to go through that now. Step 2, this KCN comes in, which can be written, of course, as that. That's cyanide. Right, just another nucleophile. Reactive nucleophile, not very bulky, secondary alkyl halide, SN2. So what do we end up with? This. All right, so you can see you actually retain the same stereochemistry as before because you did essentially 2 steps. Each one had an SN2 reaction.
All right, let's do some of these homework problems. So for this one, with the same starting material and a bunch of different ways to activate alcohols. And that's what the question is here. If you have HBr, HBr is going to do a rearrangement. That's what it'll make carbocations essentially. And so that first step, now they're not asking for the mechanism here. I'm not going to do the mechanism for all of these. But you're going to turn that into a good leaving group. And when you do that, that's of course going to leave. It does ask to make a carbocation. Now, of course, anytime you make a carbocation, you ask yourselves, can it rearrange? And in this case, it most certainly can. It's a secondary carbocation. We have the ability to do a hydride shift here. Electrons come from the bond there, so do that hydride shift. That'll give us a carbocation now as a tertiary carbon. There. And all along the way, the Br minus has been floating around. So that's where, in this case, we're going to get that rearrangement. We'll get that final product of the bromine there. Easy enough to see, hopefully. Where even though our alcohol started out on a different carbon, in the HBr or zinc chloride, they can rearrange. So we can get a product like this. Now, and we're not worried about stereochemistry because we went through a carbocation, so we actually get the bromine come from the top or the bottom, and this is in an asymmetric center anyways. PBr3, however, you should remember, that does inversion. Within the mechanism, it does inversion. So there's no rearrangement, so any site that's not on the alcohol doesn't change one bit. Drawing our wedges and hatches. Now where are these things going to be at? So if it's inversion, if the OH was hatched, now the thing that's adding, which is bromine, is going to be wedged, and the H will be hatched. All right, so that did an inversion there. PBr3 does inversions. Look at the mechanism, find that out later. We have that in other places. This one, the third one in this question was, now they use TosylCl in step 1. So what does that do? Well, if you remember TosylCl, these sulfonates, they do retention. So unlike PBr3 or SOCl2, that will do the SN2 or inversion within the same reaction. In this case, we add the tosyl group, which is shown there. So it's just abbreviated TS. And that adds there, so essentially this chlorine is gone and this piece is the TS. And then in the second step they're saying, what if you add in step 2 NaBr? What happens? Well, you're adding a nucleophile. And so this bromine can do an SN2 reaction and does inversion there as well. So let's see what that looks like. All right, I'm going to do an inversion here, so I'm not worried about where things are at. So that does a SN2 type reaction there. No rearrangements, so this is all staying the same. So now the bromine came backside. The bromine is going to be wedged, and the H is now hatched. So that'll be the final product for that too. This one takes 2 steps and allows you to add in any nucleophile in a second step you want. PBr3 does the inversion right away, gets you the bromine added there. HBr, or the zinc chlorides, they also activate the alcohol, but turn into good leaving groups and form carbocations, which then are prone to rearrangements. Right, for this, they're asking for 1 propanol, and what's going to be the final product of this. So this is in strong acid, so there's no really good nucleophiles around. So the first step is going to be a protonation. All right, so we can do a protonation. This is going to activate the alcohol. But because it's a primary alcohol, we can't form a carbocation. Right? We don't form carbocations with primary alcohols. So we can't do that. What we're going to do instead is like an E2 elimination. All right, so we're looking for those beta hydrogens. That's a good leaving group. Beta hydrogens are 1, 2 bonds away, right? And we're just going to leave. It's going to have it fall off. It's actually acid catalyzed. So these electrons will pick this H. Those 2 electrons are going to go there between 1 and 2. It's going to break the bond between 1 and the oxygen. It does an E2 elimination. All right, does an E2 elimination. What's that give us? It gives us 1 propene and water. Those are the 2 products you've made. And of course, we've regenerated H plus as the catalyst. So taking things a step further here, they want us to say we have 1 propanol, which we've seen before. Now we have 2 propanol. How can we get there? How can we work backwards from that? Well, this is an alcohol, and so let's take some time to work backwards. This alcohol, if I see this, came from an alkene. Right? And you've learned how to make alcohols from alkenes. So you only know so many ways to make alcohols. This would have came from an alkene. This alkene, right, 1 step back, could have been the product of an elimination for the product we're actually going for. So now we got to work forward. So these are all working backwards, and the question asks for 1, 2, 3 sets of reagents. So the first step to go from this to this, a strong acid would do that. H2SO4 would do an E1 type elimination, or E2. That would get us to an alkene, right? So if we number our carbons, 3, 2, 1, 3, 2, 1. And way back deep into our thinking, we got to remember, what is the way to add an OH in the anti-Markovnikov, the less substituted carbon? And that takes 2 sets of reagents. The first, you need to use BH3, and then you need to use H2O2. So this would be reagent 1, reagent 2, and then reagent 3 to get that oxidation. So you do an elimination, get the alkene. BH3 adds the less substituted carbon, and then you use H2O2 to take the BH, the boron off, and add the HOH to the less substituted carbon. That's that Markovnikov addition. All right, so here we're really trying to test our skills of understanding the way to activate alcohols and what's going on with each of those mechanisms. Now, you should be able to look at this. Right, so this is a secondary primary alcohol. There's a deuterium and a hydrogen, so there's an asymmetric center there. sp3 hybridized bond to 4 different things. And we need to be able to look at this alcohol, and if we have different ways of activating it, what happens to the stereochemistries to do that? So with SOCl2, you should look at that and say, well, I know that one does inversion. That adds a chlorine and does inversion. So that means is the product for that one would have the chlorine there, and the deuterium hydrogen not changing at all, right? So essentially, chlorine just comes from the back. You should know the mechanism to get here, but you should be able to look at this and go right to here. Now, if you add in a second step, after I made this, I've added another nucleophile. Now we can look at this. It's a classic SN2. Knocks out the chlorine. what happens to the stereochemistry then? Well, now the sulfur is there, and the deuterium and the H is there. So now we've gone from SN2, all right, to get to this, and then another SN2 to get back to here. So this is the product for that one. Different mechanism, different type of activation. The TosylCl does not do an SN2 within its initial activation, different from SOCl2. Tosyls will essentially just add, right? So they don't do inversion. They just add to the alcohol and make it a better leaving group, right? So a tosyl is, of course, this, and this is the part that's attached to the oxygen. Really good leaving group. Now in this case, now we added a nucleophile. Again, we do SN2. But you see, this whole route only involves one SN2. So we get a different product than the route above. Really got to know tosyls, sulfonyl chlorides. We go retention the first step, then we can add an external nucleophile. SOCl2, we do an inversion while we activate the alcohol, and then we could do another one. We get a 2 SN2s, gets us back to where we started. All right, for this question, it's kind of a nice review by showing a primary alcohol, essentially a primary alcohol, and all the different things you can do with it. So let's go through, and they're asking for the reagents for each of these. So let's go through clockwise and see if we can figure this out. So for this one, we're trying to turn a primary alcohol into a bromine. And so for this one, you should reach right away to PBr3. Right? That's the easiest way to turn a primary alcohol into a bromine. No rearrangements, no alkenes, none of that stuff. PBr3 does it right away. Primary alcohol to a carboxylic acid. Hopefully you remember something about chromium, right? And maybe some acid. So the chromium is those really harsh oxidizing reagents that take the H's off this carbon, make it all the way into a carboxylic acid, adding bonds, adding oxygen bonds to that carbon. But what if I want to stop it at the aldehyde? That reagent is called PCC. So you should know that one too. Hopefully you know that one too. What if I want to add a chlorine? That's that SOCl2 and maybe some pyridine. Get to that chlorine, does that SN2 within the reaction. The tougher one is this one. So we're going from an alcohol to an ether. So we're actually trying to add a carbon. So a way to do that is actually using a reagent called sodium hydride. So we're using the hydride in this case as a base. So this H minus is going to deprotonate, right, and make an O minus. And that O minus is going to be a good nucleophile. We're going to have that O minus react with methyl iodide. And that's what this carbon right here is, this carbon. So that O minus that we create from this, and the H minus takes that H, deprotonates it, makes an O minus, and then that O minus does an SN2 and gets us to this ether. So it's a nice review of all the different things we can do, kind of reagents with these primary alcohols. So another multi-step, kind of, we call these retrosynthetic problems, where here's the product, here's the starting material, and how do we actually get there? And it takes more than one step. So the way to do these, you want to look at this and kind of analyze, well, what's changed. So if I just immediately look at this, if I do some numbering of carbons, I could see 1, 2, 3, and here I only see 1. So I've obviously added 2 carbons at some point. So let's call this carbon 3. So I got to add 2 C's, right? I'd write myself that note, add 2 C's. So how am I going to do that? That's a good question. The other thing I need to think about as I work backwards, so here, look at the functional groups. So here's an aldehyde. How many ways do you know how to make aldehydes from this unit? So one step back, hopefully you think like this, would be, well, an aldehyde can come from a primary alcohol. Right? Aldehyde can come from a primary alcohol. 1, 2, 3. Right? We know one way to turn a primary alcohol into an aldehyde. Okay. So taking one step back, how do I get a primary alcohol? Like, how could I work back this way? This one's the tougher one, and of the reagents you have, it makes it a little easier. There's a drop-down menu, but if you're looking for a 2-carbon piece with an alcohol like this, one thing you want to start thinking about is ethoxide, ethylene oxide. So this is ethylene oxide. So it's the most basic epoxide possible, but it adds 2 carbons. And it's symmetrical, so I'll call this carbon 1, this carbon 1, and this carbon 2. So that's great. So that shows it's kind of breaking this bond. But how can I turn, one more step back, how can I turn carbon 3 into a good nucleophile? So right now, carbon 1 or carbon 2 are good electrophiles, right? They're electron deficient. They're reactive bonds, right? A lot of angle ring strain there. How can I turn carbon 3 into a good nucleophile, right? If these are electrophiles, this needs to be a nucleophile. Well, if you see alkyl halides, you should think, well, mate, could I turn that into a Grignard reagent? That's a good way to turn something that's attached to a bromine, a carbon that's attached to a bromine, and turn it into a good nucleophile. Turn it from an electrophile to a nucleophile. So that gives us back to our final step backwards. Now moving forward, how do we do this? So the forward reagents here would be just magnesium. That makes our Grignard. We'd have these 2 things, the Grignard and the ethylene oxide react. We'd also have to have a step where we add H+, so I'd have this is step 1. This would need to be step 2 to protonate the alcohol. All right, you can see the bond that was formed right there between 2 and 3. 3 goes there, opens up, then eventually protonate that. And how do we turn a primary alcohol to an aldehyde? Well, that reagent, hopefully you remember, one of 2 ways we know how to oxidize. PCC, that's the milder reagent that takes a primary alcohol to an aldehyde and doesn't go to the carboxylic acid. It does not go. And that gets us to the final product.